All right, lesson 4, the Bohr model of hydrogen. So what we're trying to do is trying to give reasons behind the observed spectral lines that we saw previously. We saw that a certain gas will produce certain spectral lines, a different gas at different spectral lines. And this was Bohr's model as an attempt to give reason behind those spectral lines. All right, so if you take a look at Bohr's model, so it says in order to solve Rutherford's problem of emitting EMR continuously, Bohr proposed that electrons now have stable orbits at specific radii. The electrons in these stable orbits are called stationary states and would have a defined energy, and the electrons would not continuously emit EMR in these states. There's the lowest possible, which we call the ground state, and this has the smallest orbital distance. Anything above that, we call those excited states, and they have greater energy. The highest energy is called ionization state, and if an electron reaches this, it's no longer bound to the nucleus. In other words, becomes an ion, which makes sense for ionization state. All of these are circular in nature, and they're attracted because of the electrostatic attraction, Fe. All right, we can kind of skip over this equation. Quite often we don't use this, but MVR is equal to NH over 2 pi. You can consider this to be something to do with the circumference, because we do have a 2 pi r there, and using the momentum equation. Once again, we do not need to worry about this at this point. Absorption spectra. So we talked about these absorption lines, and it says in order for an electron to move outwards to an energy with higher level of energy, they must absorb energy. The energy absorbed must be equal to the difference of the energy levels. The energy absorbed comes from photons, which are completely absorbed, or kinetic energy, which is not absorbed. The absorbed photon must have a wavelength with the energy that matches the difference of energy levels, and the absorption spectrum has dark lines that correspond to the energy that are absorbed. So in other words, we have a continuous rainbow coming through, and in order for the electrons to jump up to the next energy level, it requires energy. So in this case here, we're talking about the energy as the difference between those. We're talking about the difference in energy levels. So this value here is the energy that it currently has. It does show it up as a negative value, but then as it jumps up, it becomes a little bit less negative. So there is a positive change of energy that's occurring here, and that positive is referring to a gaining of the system, that the atom is actually gaining energy. So if you think about our regular equations for the change of energy, we usually say final minus initial, and we're going to do the same for in this case here, and we'll see how that kind of plays out. So our final energy has a negative 9.91 electron volts, and our initial energy was a negative 12. And of course, you see that the double negative kind of plays a role here. Negative 9.91 minus a negative 12 gives us a positive answer. In this case, the atom is gaining 2.09 electron volts of energy. Okay, so that is the transition between 2 to 1. And it kind of hints here that that somehow corresponds to this orangey yellow color. And it says it has a nanometers of 594 nanometers. In order to do so, we can double check to make sure that number makes sense using the same energy equation that we did previously, hc over lambda. So in other words, if I want to solve for the wavelength would then be equal to hc divided by our energy. In this case here, I want to use my 4.14 because we're talking about electron volts times 10 to the negative 15 times the speed of light, 3 times 10 to the 8, and then divide that by our 2.09 just to see how close we are to that value. Once again, there might be a slight variance just due to the fact that sometimes they use rounded values. But I got 594 almost exactly, so my wavelength here is 594 nanometers. So if you think about that energy that's required, so it take 2.09, if you look at this jump here, you can definitely tell that the energy is higher. It requires more energy to make that transition. the gap is different or larger, therefore the energy would be larger as well. So in this case here, if you think about the energy, we notice that it's 509, and 509 nanometers, even though it's a smaller wavelength, would then have more